Welcome to the 2018 AMATIC webinar series. Today's webinar is Multiple Regression from Familiar to the Multidimensional with Tom Short. This presentation is sponsored by the Joint Committee of AMATIC and the American Statistical Association. The American Mathematical Association of two-year colleges has several core values, but the one regarding professional development is building expertise and exhibiting leadership in the teaching and learning of mathematics, enhancing personal growth, and improving teaching methods and effectiveness as a personally initiated lifelong responsibility. Thank you for participating in this learning opportunity today. For more information, please see amatic.org. Please note that the views expressed by the presenter are not necessarily the views of AMATIC. Commercial products mentioned by the presenters are not endorsed by AMATIC. McGraw-Hill is sponsoring our webinar series this year. Thank you very much, McGraw-Hill. Tom has decided to just go ahead and introduce himself, so we're not going to have a biography. I'm not going to read a biography today. He's just going to go ahead and do that himself. So without further ado, I'm going to go ahead and turn it over to you, Tom.
Okay, so.
Oops, I hit a whole bunch of buttons. That was bad.
Okay, is that good?
Yep, you're good.
Can you see me?
Yep, perfect.
I mean, you can see my slides, so.
We can definitely see your slides.
Okay, so I apologize for being a bit flustered. We just spent a half an hour wrestling with a webcam that ended up not working, so I'll just have to wing it, and you won't get to see some props I have here either. So my name's Tom Short. I teach at Westchester University of Pennsylvania. I'm in the middle of my second year here at Westchester. Regression is one of my favorite things to talk about. So what I'm going to do today is try to orient you, or maybe reorient you to simple linear regression as a starting point, and then use that as a pathway into multiple linear regression. So we'll talk about some of the similar constructs and processes in those two methodologies and some of the complications that arise in multiple linear regression. So I'll be talking about two specific examples. They both have real data in them. One of them is what I call the trench data. So it's about how long should it take to dig a trench. It's a very exciting example. And the second example is from the Journal of Statistics Education Data Archive. It's about predicting body fat percentage using dry measurements as opposed to dunking somebody in a tank of water. I'll be using Minitab, but I don't have any particular association with Minitab other than just to use a standard software package to do regression analysis. So I'd like to introduce you to the trench data. This data came to me from my father, actually, who was a management consultant before he retired. And he was working on a job for a utility company. And the company was trying to establish standards for how long it should take crews to dig trenches when they were sent out into the field. So these are the real numbers my father faxed me one day, back when we used fax machines. And they represent the length of the trench in feet and how long it took to dig that trench in minutes. So in this case, we'll be using the X variable or independent variable feet to predict how long it should take to dig a trench in minutes. So I'm going to begin by exploring the data, and I made a scatter plot of minutes against feet. And I'm looking to see if there's some kind of pattern I recognize in this graph, and it's kind of intriguing. So I have to admit I was somewhat irritated when my father pestered me with this project, but I was intrigued when I looked at this graph because I think that the best model that represents it really is a line, but there's some issues with that line. So I began to pursue a regression analysis here for the minutes, the Y variable against feet. One thing I would do is describe the association much in the same way that you might start an analysis that would involve perhaps a test for means or proportions to think about how to summarize the information. So I started with a correlation, and I found a strong positive correlation between feet and minutes. And in fact, that correlation is actually statistically significant, represented by a p-value that's less than 0.001. So it's significantly different from zero. The null hypothesis would be that the correlation is zero. So I've looked at the data in a graph, and I've summarized the association with this correlation. My next task will be to actually fit a model to the data so that I can make predictions. So I'm going to fit a least squares regression line, and the notation I'll use is that the Y variable or dependent variable will be minutes, and then it will have an intercept denoted by beta 0 and a slope denoted by beta 1 multiplied by the x variable, which is the length of the trench in feet. Then there'll be these errors called epsilons, which represent the noise in the process, and there's n observations. So each one of these little equations applies to a different observation from 1 to n. Then I'll use standard formulas, or in this case, technology, to find the fitted equation. So this is when the numbers come into play. And so now instead of having a model, what I have are estimates for the slope and the intercept. And I use those to create predictions or fitted values, which are called y-hats. And at this point, if you could see me, I would put on a hat with a Y on it representing the York, Pennsylvania Revolution baseball team. And York is where my grandparents live. So I have a Y-hat that's associated with my grandparents. You can't beat that. So Y-hat represents a prediction, and Y represents a theoretical value that you might imagine. Now, I asked Minitab to help me here with the calculation, so I'm really not going to talk about the details of any calculations in today's presentation. Instead, I'm going to go on a tour of the regression output. What I think is fascinating about the way many packages present their output is that I end up reading them from the bottom up, because I think the most useful, relevant, immediate information is sometimes buried pretty far down the output. So the first thing I'm going to do is look at the bottom of the output, and I see there the regression equation. That's the fitted equation where Minitab has calculated the estimated intercept and the estimated slope. So I think there's interesting exercises to have here with students about interpreting these coefficients and what they mean and making predictions and so on. So what we learn is that we would add about 0.3 minutes to a prediction for each additional foot of length of the trench. That's what the slope might mean. And then you also learn that you can go back in time about 10 minutes if you're willing to dig a 0-foot trench. So if you forgot to do something earlier, you can just go out and dig a 0-foot trench, and the model actually predicts negative 10 minutes that you'll gain by doing that. It's pretty handy. Next, I'm going to move up to statistical significance. So after fitting the model and thinking about what it might mean and making sure that I have my y and x variables in the right place, I'm going to look for an assessment of statistical significance. And in this case, that will be a t-test for the slope of the line. And that number is 0.30102 for the coefficient, but it has a p-value that's less than 0.001, indicating that there is a statistically significant slope. It's significantly different from 0. So I sort of need some kind of filter in my practice to determine when things are worth looking at, and I find that I use statistical significance. So there's discussions now about whether that's appropriate and how p-values might not be as useful as we think they are, but I need some kind of filter, and statistical tests and p-values work for me in most situations. Next, I'm going to move up to some summary statistics. And in the summary here, I see two that catch my attention. One is denoted by the letter S, and the other is denoted by RSQ, which stands for R squared. So these values represent the estimated standard deviation of the residuals. In that case, smaller is better because we're looking for less spread around the model if possible. And R squared represents the proportion of variability in the dependent variable Y that is accounted for by the independent variables. In this case, we only have one, which was the length of the trench in feet, and we expect the R squared to be larger for better models. So I've progressed from looking at the model itself, the fitted model, thinking about its numbers, thinking about whether that important slope represents a statistically significant trend or not, and then characterizing the fit of the model with a standard deviation around the line and an R squared, which represents the proportion of variability accounted for. That proportion goes between 0 and 1. It's often reported as a percentage between 0 and 100%. So now, if I think about how I proceed through statistical tests, I usually end up considering conditions and whether I've applied an appropriate test given whether the conditions are satisfied. So the first condition I'd like to know here is that I'm using a model that's reasonable for the data. So the model is correct is what I think one of the conditions should be for a procedure like this. And then usually we impose some normality and constant variability conditions on a model like this. So in order to drive the t-test for the slope, then what we'll see is that we want the errors to follow a normal distribution. You may remember that those errors showed up a few slides ago as epsilons in the model equation before it was fitted, and that the errors have constant variability around the model, and that the errors are independent of each other. For example, that they're not autocorrelated as they might be in a time series analysis. So I want to check these conditions, and so I might use a scatter plot to determine whether the model I'm fitting, in this case a line, fits the data appropriately. And then I've mentioned the word residual before, but I didn't really define it. The residual is the observed minus predicted value. It's often denoted by EI. In fact, it's famous because the residual is one of the few statistics that has a song about it. You might know Old MacDonald had a farm, E-I-E-I-O. So there is a song about residuals. Residuals are yi minus yi hat. In other words, the difference between the observed and predicted values. You can easily check to see if the residuals follow a normal distribution by examining a histogram of the residuals, but you can also do a normal probability plot or some other assessment. I just usually look at a histogram. And then I want to look at a scatter plot, in particular what's called a residual plot, to determine whether the residuals have constant variability around the model. And then, you know, there's this issue of independence, which is kind of a slippery subject. It's hard to check it. There are some tests, but they begin to go down a road into time series analysis, and I'm not going to worry too much about that today. So now I'm going to determine whether the model might be appropriate for the data, and I see that I'm looking at a fitted line plot that was generated by Minitab. And initially, when we first looked at the scatter plot, we saw some of this behavior in the model, that it does look like there's a line, but the variability is changing as you increase in feet. So one way to interpret that is that the model is quite good at predicting how long it'll take short trenches to be dug. But when you get into longer trenches, up in the hundreds of feet here, 300 or 400 feet long, the model is not so good. And you can imagine that a utility company might bump into things and obstacles and changes in the density of the earth that they're digging through for these trenches, and that introduces some variability. So I really do feel that the model is a line, but there's something fishy about it because of the changes in variability. However, the histogram of the residuals looks pretty good. I mean, you could argue that it's not perfectly bell-shaped, but I've seen a lot worse on residual histograms. That one looks like a pretty normal distribution. That makes me happy. But then I'm going to extract the pattern that we saw in that original scatter plot and look at what's called a residual plot. And frankly, when I teach simple linear regression, it's sort of hard to pitch to the students that they need both of these, that they need a scatter plot and a residual plot, because they both kind of show the same thing, that there's this increasing variability as the trenches get longer. In other words, as the predicted times get longer as well, since there's a positive association. So the pattern that we saw in the scatter plot is represented here just without the trend in it. So you can see the opening up effect here. Of course, I think you probably already know that there's a strong motivation to teach residual plots, because when we do get into multiple regression, there won't be just one simple scatter plot to look at to see these kinds of patterns. So we need to lead the students down a path to look at these residual plots, even if they seem somewhat redundant in the context of a simple linear regression. I need to move to multiple linear regression. I need to move there soon, but I also just want to give away a little bit of the secret of this plot, is that I ended up taking the logarithms of both time and length of the trench and refit a model to the log transform data. And look at that, I sure didn't expect that. Boy, that was like the happiest statistical day of my life when I saw that, because that's a textbook scatter plot. Look at that. Look how evenly those points. So it turns out that there's some constructs in our universe that are apparently built in a log scale. And if you uncover that, you get these beautiful plots. Look at that plot. So then what I can do is look at a residual plot for that one, and you can see this sort of rectangular band of points around that line. And that indicates that this model fits well, and that some of those conditions are satisfied, that there is equal variability around that line. So I just want to show you that that's a nice little punchline to have, a motivation to look at transformed data, but that's not really the subject of this presentation. So I just want to make sure that I show you that, but then we're going to move on into multiple linear regression. So that ends my introduction in simple linear regression. And so this might be a good time if anybody has a question before we get into the multiple regression model. And I know it's not quite halfway, but are there any questions that I should address now?
So far, there's been nothing in the question and answer box at all.
Okay.
I can wait a second.
I can charge ahead too.
Okay, I think they might be good for now, but go ahead and use that question and answer box if you have any questions throughout the webinar.
Okay, so now I'm going to go into a multiple linear regression, and the example I've decided to use is from an archive maintained by the Journal of Statistics Education. And that archive has some things in it that are getting a little old now, but they're presumably real data and they can be used in classrooms. And this is certainly one of my favorites. So the premise here is that we want to estimate body fat percentage in humans. And a good way to do that is to dunk the human in a tank of water and weigh them underwater and use that value to estimate the density of the human's body. And then that density, because fat and non-fat cells have different densities themselves, that comparison with the weight underwater can be used to calculate the person's body fat percentage. So there's lots of work involved in finding drier ways to do that. And some of them are rather sophisticated, shooting currents of electricity through people's bodies and so on. And many of them have become rather accessible. This example is about taking simple body measurements and some demographic characteristics actually, and building a model to predict body fat percentage. So this represents the process of building a model to replace the real wet process of finding somebody's body fat percentage. This data set is built on a sample of adult males, and the data set is actually larger than what I'm showing you here. I've just decided to pick 5 of the variables: age, weight, height, adiposity, and abdomen circumference. So abdomen circumference is measured in centimeters, and adiposity, I think we call it BMI now. In this data set, it's called adiposity. So what we're looking at is using these independent variables as the basis for a model to predict body fat percentage. And as I said, there are more variables in the data set. I just find that it kind of overwhelms my slides and presentations if I have too many variables at one time when I'm introducing multiple regression. So the article in the Journal of Statistics Education that corresponds to this data set, so there is actually an article about how to incorporate a project like this into a class. It clarifies some of the definitions of the variables. You can see that there are more variables on the list, different circumferences from around the body, and it shows that that adiposity index is weight over height squared, and I think that's the same formula as BMI. And there actually are competing ways to calculate body fat percentage. One of them is called Broszek, and one of them is called Siri. I don't think that's the same Siri that lives inside phones. And you know, there's some options here. For example, you might do Broszek in class and ask the students to practice by fitting models to Siri outside a class. They should be similar, but they're not exactly the same. So as I said, I just picked a subset to work with, and I'm going to take that set of variables and I'm going to start going through the same steps that we saw before of trying to summarize the association and characterize it. But there's not really one graph to look at here. And I understand that there are some 3-dimensional graphs and other kinds of techniques that involve shadows or projections. But you know, I'm faced with large enough data sets that I really have no shot at seeing one graph that represents what's going on. So I'm sort of trusting my understanding of scatter plots and the associations they represent to look ahead into the statistical analysis. So I see a matrix of correlations here. I'm drawn to the first column on the left-hand side that has correlations with Broszek, which is the body fat percentage. The Broszek body fat percentage is really obtained by putting the people into water and figuring out what their actual values are. And now we are just building a model for that to use on other people, presumably, in which we wouldn't have to dunk them in the tank. This is Minitab output. It has the estimated correlation on the top row of each little cell, and then a p-value for testing that correlation against 0 on the second row of the cell. And I'd like to call your attention to two of those correlations. One of the correlations is between abdomen circumference and Broszek body fat percentage. That's a strong positive correlation of 0.814, and its p-value is less than 0.001, and so that indicates a statistically significant correlation, at least significantly different from 0. And adiposity also has a strong positive correlation with Broszek. And in fact, if I were in a classroom situation right now, I probably would take a little bit more time to explore or maybe review simple linear regression models by fitting a simple linear regression between Broszek body fat percentage and one or maybe even both of these two fairly strong associates of Broszek, represented by abdomen and adiposity. So I just want to plant that seed now. We'll come back and talk about those two in a few minutes. So now I have this multiple regression model, and the models are going to get bigger, and it's hard to write them down, and there's subscripts flying around, so it's not obvious how much of this you want to share, but this is what's going on. Is we're still trying to predict one univariate outcome, and that's going to be the body fat percentage. But our model is going to have an intercept beta 0, and then it's going to have these slopes represented by beta 1 through beta k. In this case, k would be 5, because I'm considering 5 independent variables. So this is kind of a motivation to switch away from using alpha and beta or a and b for the intercept and slope in a model, because this notation with the betas makes it easier to add more things into the notation or into the adding more independent variables. So this is a little bit more common when you get into multiple regression models. There's still an error term in the model, and there's still hats all over the place in the fitted equation. So the technology will fit estimates to these various values and give us an equation that we can use to take these fairly simple to obtain measurements from an adult male and predict the body fat percentage for that person. There's still n observations in the data set that will be used as a basis for this calculation. So once again, I'll go on a tour of the output, but now the Minitab output is too big to fit on one page. So there's going to be 2 pages, 2 screens of output here. So this is what it looks like at the top. You might see some things that look familiar, some of which we haven't yet talked about. But once again, I'm intrigued by the bottom of the output. Nowadays in Minitab, they print the regression equation at the bottom, which I think is a little bit frustrating, because it seems to me that that's what the process is all about, is finding that equation. Because that's the formula that you would give to somebody to say, here, use this to predict body fat percentage using these independent variables or X variables. So the regression equation, the fitted equation, appears at the bottom of the output, the standard output for a multiple regression in Minitab. I should also say that at least in Minitab, the multiple regression and the simple linear regression functions are the same. There's one regression function that gives you both. Let's move up above that a little bit to the top now. So for my first assessment of statistical significance, I'll look at a part of the output that we actually skipped over in the simple linear regression. Here we have this overall F-test for the significance of the regression model. It's represented in an analysis of variance table, because analysis of variance compares variability that's explained to variability left unexplained. It does that through an F statistic. In this case, we're looking at the variability explained by the regression model as a whole compared with the error variability, which is left unexplained. So what we're trying to detect here is whether the model is explaining significant variability in an overall sense. So this is something that sometimes is called an omnibus test or an overall test. I teach my students that it's like a gatekeeper or even a bouncer that's saying, look, you need to show me something before we can proceed to a deeper analysis here. And that ticket to get in is to have an overall ability to explain the variability in the model. So what we're looking at here is a p-value that's less than 0.001. It's for an f value, and I'll show you some of the hypotheses or some versions of the hypotheses that go with that test. That test now appears at the top of the Minitab output. Here are some versions of the hypotheses that overall f-test is testing. Sort of a technical version would be to say it's testing the null hypothesis that all the slopes are equal to 0. Usually they're not called slopes in a model like this. They'd be called coefficients, because a slope would really be just that one coefficient of the x variable in a line. So I might call them coefficients, but the null hypothesis is that they're all equal to 0. And the alternative hypothesis is a violation of the null hypothesis, which means that at least one of them is different from 0. So it doesn't really specify how many are different from 0, but at least one of them is. Another way to understand those hypotheses is to realize that there's a reduced model. In this case, the reduced model would have all of the x variables knocked out of it, and the only thing left would be the intercept. And so you would estimate that intercept with the average of the body fat percentages, because there would be no other x variables with which to represent any association. So one extreme case of a reduced model would be to knock out all the x variables, and that's equivalent to all of those coefficients being equal to 0. The alternative hypothesis becomes that a more complex model is necessary, reflected here by the fact that at least one of the coefficients is different from 0. So this test is really deciding whether you can get away with the reduced model or whether you do need some more complicated structure. And that idea is pervasive through all different f-tests about whether you're going to use a reduced model or whether you require additional complexity. That's kind of a theme of f-tests in these kinds of structures. And then sort of a more informal way to say it is the null hypothesis is that there's nothing worthwhile in the model. If you're in the business of predicting body fat percentage, there's nothing to see here, there's nothing worth using. And the alternative is that there is something worthwhile, and that would be reflected in having a coefficient that is different from 0. Or in this case, the alternative hypothesis is that at least one coefficient is different from 0. Then we also have summary statistics. So below the analysis of variance table with that f-test in it, we have the same little table of summary statistics that you actually saw in the simple linear regression output. These other numbers were there before, but I didn't really pay attention to them. I think that the simple linear regression output is actually simpler than what most software presents. So earlier I looked at the standard deviation, the estimated standard deviation of the residuals, and the R-squared statistic. But here I just want to call your attention to another statistic called the adjusted R-squared. The adjusted R-squared includes a penalty factor in its formula. It penalizes having independent variables in the model that aren't helping very much. So you can inflate the R-squared statistic by throwing anything into a model, and the adjusted R-squared penalizes that notion by not increasing the value as much as it might in the R-squared statistic itself. So the adjusted R-squared is appealing, and you can see in this case that it's not much smaller than the R-squared itself. And that might mean that there's some good things in the model that are helping to predict body fat percentage. So that's basically the descriptive or summary part of the output here. And then below all of this, in the second part of the Minitab output, where we initially encountered the regression equation, there's also a whole table of statistical tests. So once we've realized that there's something interesting in this model, in other words, we've rejected the overall f-test and said that there's something worthwhile in this model, now we can start to sift through the specifics. In other words, this gatekeeper or bouncer has given us permission to look at the elements in the model and sort of tease out which ones are stronger than others, which ones are statistically significant, and so on. So here what I see is that abdomen, for example, is statistically significant. It has a p-value that's less than 0.001. But for example, age is not that significant. So at least for adult males, it's not so significant in the context of this specific model to know the person's age as a predictor of body fat percentage. These tests are all conditional on the other variables in the model, and things might change, as we'll see in a few minutes, if you start to change the model structure itself. The conditions are exactly the same as they were for the simple linear regression. The model should be correct. The errors should follow a normal distribution in theory. The errors should have constant variability around the model, and they should be independent of each other. So those are the theoretical conditions, and as long as we only have one y variable, even if there are multiple independent variables, then these conditions apply because the errors, the epsilons that I've used in the notation, are univariate as well. So there's one set of errors that adjusts the predictions, if you will, from the model based on the independent variables. It introduces noise, and that noise has to follow this structure, normality with constant variability and independence. Well, you know, the data are multivariate, so it's kind of hard to check to be sure that the model is correct. There's not one scatter plot to look at. So it's vitally important to me to communicate to students that those scatter plots are a great place to see models in action, but the real world is built on more complex models that are hard to visualize. So it's kind of hard to see some of the structure that's going on in these complicated models. However, there still are residuals, at least if you only have one y variable in the model. There's still a residual. It's called EI. It still has a song about it. And so you can look at those residuals. They're still univariate. And you can make a graph of those residuals to see if it's normal. And you can also make a residual plot. So as I mentioned before, it's important to introduce residual plots and make the connection to a scatter plot in simple linear regression. But because now that's going to be the tool we use to determine this, whether the model really is correct and whether properties like equal variability are appropriate. Look at that. Look at that histogram of the residuals. That's a nice looking normal distribution. Well, it's got some spikes in it, but if you squint a little bit, it sure looks bell-shaped to me. So it's real data, and it's behaving the way we would like it to behave. And look at this. This is a pretty good residual plot. Remember that on the y-axis we have the residuals, and then on the x-axis we have the predictions that are generated by the model. In the trench data, this opened up as a triangle, indicating a problem with unequal variability. In other words, it was easy to predict how long it would take to dig short trenches, but hard to predict accurately, or at least without variability, for longer trenches. But here what you see is that for all kinds of body fat percentage predictions along the x-axis, there's essentially constant variability. There aren't that many people in the study who have large values for their predictions. Presumably that corresponds to large values for their body fat percentage. So the right-hand side of the graph is not as filled out, it's not as populated, but I still don't really see a dramatic change in the variability around that center line. So this graph represents a check of the conditions even in a situation when you have a multivariate model predicting a y variable, in this case body fat percentage. All right, now we want to talk about some of the complexities that arise in fitting multiple regression models. I want to take you back to that slide that showed that both adiposity and abdomen percentage, abdomen circumference, they both have positive and statistically significant correlations individually. So even though these correlations are all measured or reported in one table, they actually represent different associations between Brozek and these independent variables. In fact, the whole table also shows associations between independent variables themselves. But obviously, we're interested in predicting Brozek body fat percentage, so the first column is a good place to look for that. Now you get to see some of my artwork. So one of the big analogies I use in my classes is that what we're going to do is explore a forest of regression models. So I want to communicate to my students that regression is a messy business. It's like wandering in a forest, except that we are able to organize that forest. So on the left-hand end, if you want to consider it the west end of the forest, there's a series of trees, and those trees represent univariate models. Each one of them is based on one of the x variables. So for example, x1 would be age, but there's 5 of them in this case. So there's basically 5 trees, if you want to think of that as 5 entryways into this forest. And then the other end of the forest is something that you might call the full model. That's the model that I actually fit for the multiple regression. It has all 5 of the independent variables. So this forest is a place where we need to wander, and we're going to be looking for Grandmother Willow. If you remember from Pocahontas, Grandmother Willow is the talking tree that dispenses life lessons. So that's the best model in the whole forest as far as I'm concerned. And so we're looking for that model. We're starting in maybe different places around this forest and hoping to find pathways that would lead us to either Grandmother Willow or comparable models. So the trick in multiple regression is to develop strategies or adopt strategies to navigate the forest in a way that leads you to good models, no matter where you start, or perhaps to different good models depending on where you start. So that's one important analogy to communicate, is that, you know, you need to be able to navigate a forest, and the forest can get a little bit scary. Another analogy I use is this moving analogy. So here are 2 strong movers. Sometimes I tell my students that this is my brother and me, and I ask them which one is which. And obviously they see me and they can tell that I'm the one with hair, and my brother doesn't have as much hair. So we're both strong movers, and we're ready to help. We're ready to help move big pieces of furniture. We're unloading the truck now. You can see how good we are. We're happy. We're both cooperating here. We each have heavy ends of the sofa that we're moving into some apartment. Unfortunately, we're moving it to the 3rd floor of an apartment with no elevator. And so we have to carry it up these narrow stairs. And when that happens, we get into this situation where the person on the bottom of the sofa is basically doing all the work, and the person at the top, even though that person is a strong mover individually, ends up being put in a position where we're not taking advantage of their strength. The strength is all being supplied by that mover on the bottom, and the one at the top is basically just steering. So we began with 2 strong and independent movers, and what we've ended up with is a situation where we're not really taking advantage of their individual strength, at least for all of them. So this becomes an important analogy for me to teach about multiple regression. So I'm showing you another regression output now. This one still has Brozek body fat percentage as the y or dependent variable, but now it has only those 2 interesting predictors in it, adiposity and abdomen. And often I'll let the students guide me to this, because what we'll do is we'll fit a simple linear regression using abdomen, since abdomen circumference was the single strongest correlate of body fat percentage. And then I'll ask, well, if we're going to navigate this forest, what path should we take? What should be our next model? And usually somebody will say, well, let's put in adiposity, because it was the 2nd strongest correlation with body fat percentage. So we did that. We put in adiposity and abdomen, and this turns into the beginning of a pathway into the forest of regression models. And so now what we see are these tests. We see tests for the significance of these 2 individual predictors, abdomen and adiposity. And this is fascinating, right? So this data set seems a little bit old-fashioned, because now we have scales for example, that shoot electric current through you to measure body fat percentage. But look at what happens here, because we started with these two independent movers, if you will, that called adiposity and abdomen. They both had strong and significant correlations with Brozac. And now what's happened is that abdomen has maintained its significance, but adiposity has not. The p-value for adiposity is now 0.091. And in fact, its coefficient has changed to be negative. It had a positive correlation with Brozac before, and now, you know, that correlation is not significantly different from zero. So in some sense, you can just interpret it to be a zero, or at least not significantly different from zero. But that strong individual mover isn't doing any work right now, right? So abdomen is doing the heavy lifting. Abdomen is at the bottom of the sofa, and adiposity is just basically steering now. So that's a little bit scary, right? That's why the forest becomes scary, because we were screening those predictors at the beginning, and we realized that both of those look like strong individual predictors, strong individual movers in my analogy. But when you put them in this particular situation, we're not taking advantage of their combined strength, or at least their individual strength, because adiposity is not even a significant predictor in this model. Oh, so that's interesting, because that means, you know, the assessment of significance and so on is changing as you move through this forest of regression models. That effect is called collinearity. In fact, you could see that collinearity. I was trying to draw your attention to the left-hand column, but in fact, out there on the right-hand side is the reality that adiposity and adiposity is BMI and abdomen is a circumference, but they have the single strongest correlation in the whole table of 0.924. That's called collinearity. That means that those two independent variables are collinear. In other words, they have a strong correlation. They're not really so independent of each other. You could also have a construct called multicollinearity, which means that the relationship is more complicated than just two. It might involve basically a linear relationship or some other kind of function that includes many different independent variables. But the beginning of that is this thing called collinearity. So if I ask you, tell me what collinearity looks like, you can all chant together, this is what collinearity looks like. And in the graph, you can see the super strong positive association between abdomen and adiposity with that strong positive correlation. So, I mean, that looks like a nice scatter plot for fitting a model, but it wasn't really the aim of this study. We assumed that those were kind of independent indicators of body fat percentage, and in fact, they're not. And that causes problems with assessing significance and the relative importance of these predictors in the context of specific regression models. So we have to develop strategies for navigating this forest, and this is the entree into all kinds of methodologies in multiple regression that just don't show up in simple linear regression. So one of them that is connected between the two is to look at residual plots. I really like the analogy of the forest of regression models, because I'm basically surrounding the interesting models in between. I'm saying I'm going to start with some simple regression models on the west or left-hand end of the forest, and I have this big model on the other end that has everything in it. But that establishes bounds for my R squared, and it helps me to realize that the residuals are behaving the way they should. And so I'm basically surrounding the interesting models in between. I'll always try to maintain statistical significance. I find that if you don't have significant effects in your model, or if you leave things in the model that are not statistically significant, it leaves your analysis open for criticism, even if there's good reasons for perhaps considering non-significant effects. So I don't like to be called out when I'm giving a presentation because somebody notices that I have a non-significant effect in my final model. So I often use significance as a filter, I have to admit. I'm going to monitor those summary statistics to make sure I'm still looking at essentially pretty good models, even if they're not at either end of the forest. And the really big issue is that maybe you're in the wrong forest, right? That's really a scary thing, because the forest you're in is scary enough, and then the next thing you know, you might be in the wrong forest. That trench example shows that transformations might change your forest. You might introduce interactions or powers, which are sometimes called second order or higher order effects. They're basically multiplications between your independent variables. There are other strategies called things like principal components analysis or latent variable analysis, and those might help you to combine the effects of things like adiposity and abdomen circumference to represent some common structure so that they wouldn't bump into each other like two independent movers, but rather would represent their strength in a combined or even like an average kind of fashion, depending on how the units would combine. So these are all issues as you consider navigating the forest of regression models. Remember that I think it's important to realize that if you start at the simple end with simple linear regression and at the complicated end with a full model, the full model means you're going to throw everything you have into that model and consider that the biggest tree in a forest, but then try to celebrate parsimony. That means that you're going to try to aim for things that are simpler. Simpler might be better. One filter for that is statistical significance. Try to lean toward interpretability when possible so that somebody can look at your model and say, hey, that makes sense. Those effects make sense in explaining the dependent variable. There are methods built into software to do automated variable selection. Sometimes those are called stepwise methods, and I actually use those, but I use them to help me explore a big forest just so I don't miss corners of it that I would otherwise miss. So I use them to sort of produce candidate or competing models with models that I find myself or that a content expert suggests might be good models. So I use a variety of methods, and often I don't find just one model. I find some candidate models which all seem good. In other words, good trees in that forest, and I might monitor them. I might let them make predictions for a process that's continuing over time and monitor which ones are making good predictions. Does it matter which one I choose? Sort of putting them into a contest to see which one holds up the best, making predictions in the future. So that's my presentation. I hope that you appreciate this introduction to multiple regression and that you can guide students into the scary forest of regression and find Grandmother Willow. Thank you.
Thank you, Tom. There were two questions, but I think you may have answered them during the presentation. So I can give us a hint here. Let's see. One of the questions was, remind us what the dependent variable is. And I wrote down that it was when you had that slide up the first time with describe the association through correlations with the age, weight, height, adiposity, abdomen. So right. I don't remember anything else. I'm sorry to try to give you reference.
So we have a target, and in the two examples I did, the target in the first example was that we wanted to tell a crew how long it should take them to dig a trench based on how long the trench was. So right. The dependent variable is the time, and it depends on how long the trench is. And then in the body fat example, what we're trying to do is predict the body fat percentage using these other variables. So presumably body fat percentage depends in some way on the independent variables. So it's usually denoted by Y, but it's a thing that depends on the other variables.
Okay. The next one, and it was, I think, around the same point of the presentation, is if the correlation matrix shows there is no correlation between U, IV, and DV, which I think is Brozek, do you take it out of the model?
Well, so that's an intriguing question, simply because we've already seen that that some of those patterns of significance can change. Now, I live in a reality where I have deadlines, and so I can't afford to wander into every corner of this forest of regression models. And so I admit that I certainly would consider dropping variables from consideration if they don't even contribute any kind of substantial correlation with the dependent variable at the beginning. So I even sort of did that in this case because the body fat data set actually is larger than what I've presented here. It has other body circumference variables in it, and some of them are likely to be correlated, but partly because I just don't have the screen space to show them all or the time to wander too much, I reduced that set. But it is true that you might cut variables from the very beginning, basically to save time and to shrink that forest down a little bit, assuming that they would not regain or achieve any kind of significance later on.
Okay. A few more are rolling in. Let's see. Do you ever use the VIFs for assessing multicollinearity?
Yeah, sure. So VIF is a statistic, and I think it actually has been showing up on the Minitab output as a default, which is a little bit surprising. But yeah, it stands for variance inflation factor, because one effect of multicollinearity is variance inflation, and those values can indicate where the collinearity exists. And so big values of VIF might guide you to look at specific relationships, especially in larger models where there are just many, many independent variables. It might highlight those kinds of relationships. So yeah, I do use those.
Okay. Another question, if you do use a correlation matrix as the starting point and there's no significant correlation between an IV and the DV, should you remove the IV from the model from the outset? And is there a cutoff for the correlation coefficient?
Well, I think we talked about that similar question just a couple minutes ago, but
right.
Yeah, I mean, I really do feel like statistical significance helps me to filter out things that are worth considering downstream. So I don't mean that I always use the same threshold depending on where I am in a model building process. That I might not always use 0.05, I might use a higher level. In fact, when you look at stepwise type procedures, you can control that and maybe be a little more generous in letting things hang around at the beginning of a process. But yeah, I'm willing to simplify the problem by cutting things out from the get-go.
Okay. Is this topic introduced in an introduction to stats class? If so, what topics are then taken out?
Well, I mean, I think that multiple regression is an intriguing topic, much like analysis of variance, because they are usually not taught in an introductory course, or at least they're not part of the standard syllabus. They're not part of the AP statistics syllabus. So basically courses that don't reach multiple regression or analysis of variance, they're interesting. They introduce students to statistics, but they get to this big river, and you might look over to the other side and see multivariate analysis, but you don't get to do it. So I really like to highlight these connections between simple linear regression and multiple regression. I like to highlight connections between t-tests and analysis of variance, because so many methods past the intro course are based on these kinds of structures. In fact, in some ways, you can phrase almost anything in statistics in terms of a regression approach. So I think it's good to expose students to it, but I admit that you don't really have time. It's not an easy task.
Okay, I think you answered this, but another question came in. It says, if you find multicollinearity, is it okay to remove one of the offending variables?
Oh, that's fascinating. So multicollinearity means that there's some complicated structure, like a functional structure, almost like a regression model, that relates independent variables regardless of whatever connection they have to the dependent variable. So the word collinearity to me means two independent variables are related, but multicollinearity means that there's some complicated function in there. And it is true that sometimes mathematically you can pull out one of those independent variables and it'll basically break the spell of the multicollinearity. And that's good. But to me, that's a little bit mechanical. Really what happened there was that you had some structure in your independent variables, and you might want to step aside if you have time and do something like a principal components analysis or some other way of recognizing that structure rather than just kind of pulling the plug on one of the variables.
Okay.
But it depends on how much time you have.
Okay. Okay. Last question. Can you provide a conceptual description of what the computer is doing to develop the betas for multiple regression model, something that might help us explain this to students?
Wow, so I try to avoid explaining that, because because I can show them least squares regression in a simple linear regression context. There's nice applets available online where you can actually see the squares and think about minimizing the sums of their areas. And that same principle applies to multiple regression, but to make the language mathematically concise, you really need to represent those in matrix notation. There is linear algebra involved, and you don't really have to talk about the specifics of the linear algebra, but you really kind of need vector and matrix notation to communicate the complexity of the structure. So it's hard to explain the math of it, and that's why I rely so much on technology.
Right. Okay, thank you so much, Tom. You've gotten tons of thank yous already in the chat window. We certainly appreciate your presentation today. Attendees, please don't leave quite yet. I have a little bit more to do with you guys. Let's see. And I goofed this up, so let's see if I can fix it. Maybe. Perhaps. Thank you for participating in today's webinar. If you'd like to support future AMATIC webinars, please consider becoming a member of AMATIC. You can always go to bit.ly/join-AMATIC. We are on Facebook. We're also on Twitter. Each of the regions also has Facebook groups now, so check us out. Recording. So there were a couple comments in the chat window about recordings of today's webinar. Yes, it was recorded. It takes usually about 1 to 2 weeks to get that processed and up for you, and you will get an email from me when it is ready. If you could please take 2 minutes to evaluate the webinar content and the presenter by going to bit.ly/amatic66. I will also go ahead and put that in the chat box for you. So hopefully I don't have a copy and paste fail. No, I did not. That was wonderful because last time I did. So if you need a certificate to say that you were here today, please make sure that you fill out that survey because that's how you are going to get it. I'm going to go ahead and stop the recording, but I won't get off yet. If I can find that. There we go.